Descriptive statistics, statistical tables and graphs. The collection of data is just as important as how we interpret it. Descriptive statistics is what we refer to as the collection, summarization, and display of data from a sample. If you recall, datasets can consist of two types of data, qualitative and quantitative data. Quantitative data consists of numerical measurements or counts and can be further described by distinguishing between discrete and continuous types. Discrete data result when the number of possibilities is either finite or a countable number such as 0, 1, 2, 3, or 4. Continuous data result from infinitely many possible values that correspond to a continuous scale. There are no gaps or jumps or interruptions. Qualitative or categorical data consists of attributes, labels, non-numerical entries, or categories for which we can classify data. We can further differentiate data by characterizing their level of measurement. Data at the nominal level of measurement are qualitative only and are categorized using names, labels, or qualities. Data at the ordinal level of measurement can be qualitative or quantitative and can be arranged in order or ranked, but the differences between data entries are not meaningful. Data at the interval level of measurement can be quantitative and can be arranged in order or ranked, and now the differences between the data entries are meaningful. A zero entry is possible, however this zero entry simply refers or represents a position on a scale and has no meaningful representation. Data at the ratio level of measurement can be quantitative and are similar to the interval level of measurement with the added property that a zero entry is now meaningful. Meaningful zero indicates you have none of that particular data. There are many ways to organize and describe a data set. Important characteristics to look for when organizing and describing data sets are its center, its variability or spread, and its shape. A data set has many entries, it can be difficult to see patterns. A frequency distribution is a table that shows classes or intervals of data entries with a count of the number of entries in each class. The frequency of a class is the number of data entries in that class. The relative frequency of a class is the portion or percentage of the data that fall in that class, typically represented as a percentage. The cumulative frequency of a class is the sum of the frequencies of that class in all previous classes. The cumulative frequency of the last class is equal to the sample size. Let's take a look at an example. A teacher makes the following list of all the grades she gave to her 25 students on an essay. This list contains all the grades, but it isn't easy to read. A better way to display these data would be with a frequency distribution. Let's see the steps necessary to create a frequency distribution on the next slide. In a frequency distribution, the first column lists all the categories of the data. In this particular case, we're referring to the letter grades of A, B, C, D, and F. The frequencies, remember, are the number of data entries that fall within each one of those categories. So we see, if we refer back to the previous slide, there are 4 A's, 7 B's, 9 C's, 3 D's, and 2 F's. The total should be the entire sample size of the 25 students in the class. Our next column, the relative frequency, is the proportion or percentage of the data that fall in that class. If 4 students received an A, 4 out of 25 gives me 16%, or we'd say roughly 16% of the students received an A. And we repeat that process for the next grade category. 7 students received a B. 7 out of 25 gives me an overall percentage of 28. So we claim that 28 students received a B on the essay. The total relative frequency should always sum up to be 100%. The cumulative frequency is the sum of all the frequencies of that class and all previous classes. Recognize that the first entry for the cumulative frequency is going to be the frequency for just that class. However, from here on out, we're going to be adding the frequencies together. So the cumulative frequency that we want to find next would be the total number of students, or the total frequency of individuals that received a grade of A or B. So 4 plus 7 would give me a cumulative frequency of 11. Another way that we can interpret this value, we would say that 11 students received an A or a B. If we keep adding the next frequency, we get the cumulative frequency for all of the students. Remember, the cumulative frequency of the last class should be equal to the sample size, or in this particular case, a total of 25 students. Bar graphs and pie charts are commonly used to display qualitative data. A bar graph uses a set of bars to represent the frequency of each category. The higher the frequency, the longer the bar. Pie charts are primarily used for relative frequencies because the total pie must always represent the total relative frequency of 100%. Notice on a bar graph, the bars can be vertical or horizontal. Clear labeling is important here because without proper labels, a graph is meaningless. The graph should have a clear title, vertical and horizontal titles, as well as scales to indicate the differences between each one of the values, and a legend if multiple bars are included. A pie chart can also be used to represent qualitative data representing the relative frequency of each one of the categories. Notice that the size of each wedge is proportional to the relative frequency of the category it represents. This example showed how a frequency distribution can be used to display qualitative data. However, a frequency distribution can also be used to display quantitative data through the use of classes or intervals in order to group data together. Each class has a lower class limit, which is the least number that can belong to the class, and an upper class limit, which is the greatest number that can belong to the class. The class width is the distance between the lower limits of consecutive classes, and the range is the difference between the maximum and minimum data entries. Let's take a look at an example, this time dealing with quantitative data. The dataset below lists the price in dollars of 30 portable GPS navigators. Construct a frequency distribution that has 7 classes. Since the minimum data entry is 65 and the maximum data entry is 340, the range of this particular set of data is 275. This means that we would like to create 7 classes that can encompass all possible values. By dividing 275 by 7, the number of classes stated in the problem, we get a class width of approximately $40. Let's see how that's going to help us create our frequency distribution. Notice all of our columns remain exactly the same except for the first one. Instead of having a category type, we're going to have a class interval here. The minimum data entry is a convenient lower limit for the first class. To find the lower limits of the remaining 6 classes, add the class width of 40 to the lower limit of each previous class. The frequency is exactly the same as it was before. It's going to be the number of data values that fall within each interval. Portable GPS navigators that fall within the price range of $65 to $104, there were 6 such GPS navigators. Relative frequency is calculated in the exact same manner. 6 divided by 30 gives me 20%. We claim that 20% of the GPS navigators in our sample fall within the price range of $65 to $104. Notice we had to round a few of these values, so the relative frequency is going to be approximately 100%. Cumulative frequency, again, is calculated in the exact same manner. Cumulative frequency is the sum of the current class's frequency and all classes above it. Remember, the cumulative frequency at the last class is equal to the sample size. A frequency histogram is a bar graph that represents the frequency distribution of a data set. Few things to keep in mind. Number 1, the horizontal scale is quantitative and measures the data entries. The vertical scales measure the frequencies, and consecutive bars touch. A histogram is essentially a bar graph in which the data categories are quantitative. The bars on a histogram must follow the natural order of the numerical categories, and the widths of the bars have specific meaning. The bars in a histogram touch each other because there are no gaps between these categories. A line chart, or frequency polygon, shows the data value for each category as a dot and the dots connected with lines. For each dot, the horizontal position is at the center of the class interval it represents. A newer way to display quantitative data is called a stem and leaf plot. In a stem and leaf plot, each number is separated into a stem, the leftmost digits, and the leaf, the rightmost digits. You should always have as many leaves as there are entries in the original data set, and the leaves should be single digits. A stem and leaf plot is similar to a histogram, but has the advantage that the graph still contains the original data and provides an easier way to sort it. Let's take a look at an example. The data set below lists the number of text messages sent last week by cell phone users on the first floor of a college dormitory. Construct a stem and leaf plot. Because the data entries go from 78 to a high of 159, you should use stem values from 7 to 15. To construct the plot, list these stems to the left of a vertical line. For each data entry, list a leaf to the right of its stem. For example, the entry 155 has a stem of 15 and a leaf of 5. Make the plot with the leaves in increasing order from left to right and be sure to include a key. From the display, we can see that more than 50%, 28 out of 50 of the cell phone users sent between 110 and 130 text messages. In stem and leaf plots, we can more easily identify unusual data entries called outliers. In the weeks to come, we will identify how we can calculate and interpret these outliers.